Sir, good afternoon, sir. Govindraj, sir, good afternoon.
Very good. Sir, very good afternoon.
Good afternoon.
Good afternoon, sir.
Good afternoon, Dr. Bharat, sir. Good afternoon, Dr. Eldon.
Sir, our Varla, sir, he'll be coming shortly.
Hello?
Yeah, good afternoon, Dr. Eldon. Welcome.
Yes, sir.
Yes.
Bhaskar, how are you?
Yeah, I'm fine, sir. I'm fine. Nice to meet you.
Yeah, nice to meet you also. Yeah.
Yeah.
No, I'm sorry. I was not here. I just came because I have to connect to the docking station. My
No problem. Yeah.
no, I'm sorry. I was not here. I just came.
Otherwise, you are in
because I have
Rotterdam.
to connect to the
You
docking
mentioned this
station.
is Rotterdam,
My
sir.
computer.
Yeah.
No, I was not here. I just came.
Otherwise, you are in Rotterdam. From Amsterdam,
Dr.
it is 1 hour journey, yes, sir? From Amsterdam.
Yes, sir. Yeah.
Dr. Eldon, good afternoon.
Yeah. Hi, Govindraju, how are you?
Fine. How are you?
Yes, I'm good. And how are your parents? Because I heard that they were a bit sick. Yeah.
Okay, all right. They are improving. All right.
Okay.
Okay. Now they are slowly improving. Somewhat okay.
Hmm.
Okay. How are you? How are your family members?
Yes, they are good. Yes, I just spoke to my mom this morning.
Okay. Fine. Okay. Are you visiting India? You said recently?
No, it was the last year when I saw you. Yeah.
Oh, okay. Yes.
Hmm.
Okay, fine. So we are so much thankful to you for accepting our invitation.
Okay. No, I'm very happy that you had invited me, and it's a great opportunity to also attend this conference and to know
Okay.
the dates of what you're doing.
Okay. Thanks a lot. Fine. How about COVID in Netherlands?
Now it is decreased. It has decreased a lot because of the vaccination. Yeah.
Oh, okay. Very nice.
They have made Pfizer available, isn't it, sir? They have made
They have Pfizer and also three other yes, AstraZeneca and another one I cannot remember the name.
okay.
So,
Pfizer, they
yeah, but it all depends on the age group and also the people with any other symptoms or other things. So,
right, sir. Okay.
so it's not the same, and we cannot also ask that I want this. Yeah, it's all the government that decides, and also
What they decide.
the head doctor who will decide based on your health. Yeah.
Yes.
Okay. Very nice.
Yeah, because it is not in the private control; it's all in the government.
Government.
Only when they invite, we can go and put the vaccine. Yeah.
Vaccine.
Sir, are you able to see my screen?
Yeah.
Okay.
It's visible, sir. Visible.
Yes. Yeah. Okay. Perfect.
Yes.
And is it moving now? Just to confirm.
Oh, not moving.
No.
Not moving.
Oh.
Yeah. Now it's moving.
Yeah.
Yeah. Now it's okay.
Okay.
Okay. Fine. You spoke to any of your friends?
Yes. Sometimes I speak, but it's very difficult to
Okay,
Be in touch
okay.
because everyone has their own priority now.
Yes, 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 yes. Okay, fine, fine. Basta sir, you will start by 8:30 exactly. Basta sir, Dr. Bhaskar. Rajshekhar are ready, no? Rajshekhar?
Yes, sir. Yes, sir.
Okay, okay, fine, fine, fine. Rajshekhar,
Sir.
you put a message in our WhatsApp group.
Yes, sir. Okay, sir.
Okay, okay.
Sir, I have posted in the students group, sir.
Okay, okay, thanks, sir. Thank you, thank you, thank you. Thank you. Eldon,
Yes, yeah.
yeah, you know, Dr. Mr. Madam Sivanachali, you know, Sivanachali? Are you remember?
Yeah, yeah, from Anomaly, right?
From Annamalai.
Yeah.
She resigned doing our course itself, no? Resigned for due to marriage.
Okay.
Oh, she joined in our college as a faculty.
Oh, okay, okay.
This month. She got a break from Annamalai University. Then he switched to PhD at Anna University. And she was a woman scientist award. There are so many awards at Anna University, ACTech. She was there for more than 15 years in Anna University. After completed PhD, now last week he joined in SUC as a faculty.
Okay, yeah, very good.
Yeah.
And what was your specialization?
That not much clear. Yet to meet her, but everything is under online only we are doing. And maybe in ACTech, no, what is that? Always separation, mass transfer, environmental. I don't know much exactly what is the area of specialization. I will inform you after meeting her.
Okay, yes, yeah.
So we are happy. Our teacher is joining with us. That's happy.
Yes, yeah. I was only in touch with Professor Mullai madam. Yeah.
For Mullai. Mullai. Mullai is junior to Sivanachali.
Yes.
Yes. Then recently only I have promoted as a assistant HOD of department.
Okay. So you have a lot of administrative work now.
Yeah, almost. It's a post is called assistant HOD. Recently appointed.
Okay, very good.
Okay, thank you. Everything is because of our blessings. You do any cooperative work with Mullai madam?
No, in the past I used to do, but I'm only in touch with her now. Yeah, but we are not doing any project. But they had projects with RMIT in Australia. Yeah.
Okay.
So I know that group from RMIT. It's Professor Jagadishan and Professor So yeah, I used to work with them. No, I'm still working
Okay.
with them, but but
Okay.
they have very good links with Annamalai University. Yeah.
Fine, 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 fine.
Yeah, because they had a big project that was aimed at zero liquid discharge for
Okay.
the textile factories in
Oh,
Tirupur. Yeah.
okay. Okay.
Mm. And also I think Liji Philip madam, Liji Philip from IIT Madras. I think she was
Yeah,
also there.
yeah.
Mm.
Fine, fine, fine. The Mully madam, you became a senior now. Next RDS now, RDS, Dhanshed sir, RDS.
Yes. Yeah, yeah.
Hi, hi. He will be the next HOD of Annamalai.
Mm.
Next to that, Mully only is there.
Okay, okay, yeah.
Oh, okay, okay.
And
Senior
then
most professor in
yeah, and then it will be Ravi sir. Yeah.
Ravi is after Mully.
Yes. Yeah, you're right.
Yes, yes. Ravi is our own senior now, 1 year senior now, Ravi.
Mm-hmm, mm-hmm.
Ravi. Mully is senior to Ravi.
Yeah.
Yes. Is it your office? Yeah.
Yes, yes, yeah. This is my office. Yeah.
Oh, very nice.
No, it's better to come to the office. Although most of the staff members have the option of working from home, but for me,
Oh.
I think it's better. And also I'm alone, so it's very boring in
Fine,
the
fine.
house. Mm.
Yeah, of course, of course. Dr. Bhaskar?
And Govindarasu, can you see my screen?
Yeah, I see. It's visible.
It's moving. Yeah.
Yes, it's moving.
Okay. Okay. Good.
Yes, Govindraj sir.
Sir, shall we start, sir?
Yeah, so one thing, Dr. Rajashekhar is introducing, no? The chief guest.
Yeah. Yes, sir. If you are ready, I will ask Ashay to introduce.
Lavanya, are you there?
Yeah,
Sir,
sir.
participant
can,
list only.
You can ask.
Participant.
Rajashekhar is giving the intro. Yes, Professor Govindraj.
The participants are very less, sir.
We can wait for 2 minutes. We can wait.
Yes, sir. That's what I'm saying.
Our people are having lunch. They will be joining shortly. They have completed the sessions. There is maths or what?
செஷன் டிலே பண்ண வேணாம் ஏன்னா இருக்கும் they will join நீங்க தொடங்கி ஏன்னா அவங்க அதர் கண்ட்ரில இருந்து இது பண்றவங்கள நம்ம let them not wait.
Okay.
Okay.
So,
Let me start, sir.
sir.
Yes, sir.
You can introduce the chemistry HOD, sir.
Good morning. Good morning, Professor. Myself, Dr. Thiosulfate, I am HOD Applied Chemistry. Very nice to hear from you.
Yeah, thank you, sir. Yeah, thank you. Thank you so much. And indeed, it's also a great pleasure for me to join this international conference on green materials and renewable energy online. And thank you for the invitation. Thanks.
Thank you. Thank you.
Yes, Lavanya, you can start the proceedings.
Okay, sir. A very good afternoon to one and all present here. I would like to extend my warm welcome to you all for the online international conference on green materials and renewable energy. I would like to call upon Mr. Rajashekhar, Assistant Professor, Department of Chemical Engineering, SPCE, to introduce our chief guest, Eldan R. Rini, IHG, Delft Institute for Water Education, Netherlands.
Thank you, Lavanya. Good afternoon, everyone present here. I welcome respected dignitaries and respected chief guests and participants. I welcome all of you to the afternoon session of the second day of the International Conference on green materials and renewable energy. It is honor to introduce chief guest Sri Eldan R. Rene. He is currently working as a senior lecturer at IHG Delft Institute for Water Education in Netherlands. He obtained his university teaching qualification diploma from IHG Delft and a PhD in chemical engineering from the Indian Institute of Technology, Madras. Biological processes for waste gas and wastewater treatment, development of waste to energy conversion technologies, and and the use of artificial intelligence tools for environmental monitoring and environmental process management. As a part of his educational and capacity building efforts, Eldon regularly teaches scientific writing and skill development MS and PhD students in major international events and conferences. With this small introduction, I welcome Sri Eldon R. Rere for delivering keynote address. Thank you, sir.
Thank you very much for the nice introduction, and indeed it's a great pleasure for me to talk to all of you who have also a background of chemical engineering or environmental engineering, and so that's very easy for me to give this introductory lecture where I will share some of my experiences with bioreactor configurations for the treatment and resource recovery from waste gases. Okay. So I would go directly, before I go into the presentation, first I would start to tell a little bit about the institute. So you can see here that I'm working at an institute called the Institute for Water Education that has a long-standing partnership with the United Nations, which has its head organization based in Paris. So we were a part of the UNESCO for quite some time, and it was one of the largest, and it is the largest water institute in the world. And this is the building that you see. It's not like your campus. It's not a very big campus, but it's just a building that's in front of the train station of Delft. So Delft is a city that is almost 1 hour from Amsterdam, the main, the capital city of the Netherlands. So this institute, I would like to, for the next couple of minutes, I would like to tell about the institute, what are we doing and what is our mandate, because I think it's very interesting, because we work on projects that are mainly related to developing countries, and specifically now we work a lot with India and also in Southeast Asia and other countries. So that, as you all know, there is always a need for water professionals from all over the world. It doesn't matter whether you have a lot of water or whether you don't have water, or whether you're located in a city which has water conflicts or water related issues. Okay, so when you have a lot of water, it is also a big issue. When you also have water scarcity, then there is also a big issue. And in some cases, as you all know, we have a lot of rivers that are also transboundary in nature. And one of the classical example is the Mekong River that flows all the way from China to Vietnam. So when you look at such mega rivers, you always have a big risk of floods. You have contamination. You have also problems at the geopolitical level. So in many cases, we work closely with these countries where they have problems with water. So as you know now, the Sustainable Development Goals, they are also very much linked to water and health. So we also try to combine water with sanitation and water also with the environment. And at IHE, we are mostly working on water-related issues that can go from water politics to water governance. But I'm not into that field. So I work mostly on the development of biotechnologies or bioreactors for resource recovery from wastewater. Okay, so this institute was established in 1957, and we have a lot of alumni, and there are at any given point of time when you come to our institute, you can at least see people from 150 countries. Okay, it's a very international institute, and most of them are from the developing world. And the mission of our institute is to strengthen the capacity in the water sector in order to achieve the sustainable development, or in order to also realize the SDGs. So we focus, just like also your university, we also focus on education and training, but we don't have education at the bachelor level. We only have masters and PhDs. And we do a lot of specialized trainings, what we also call as tailor-made training. And these tailor-made trainings can be for a group of teachers, it can be for a group of different stakeholders, it can be done at your organization, or if we have funding, we also invite them to come to our institute, and we give this specialized trainings. And then we also work with research and innovation, and also with institutional strengthening activities. So I would like to just focus only on this before I go to our topic. Okay, so if you might be interested, maybe in the future, we could also apply for some specialized TM80, which we call as tailor-made advice and training. And this can be for 1 week, or it can be 10 days. And we can apply for different fundings, that is from the World Bank, or we can also ask the DST or DBT from India, that has collaboration with the NWO in the Netherlands, and also with the NUFIC, that's the main funding agency in the Netherlands. So this is something that is really nice. So it all depends on the requirements from the organization that is requesting. So for example, we did a 1-week training on environmental monitoring of heavy metals in Barbados. Then there was also 3 weeks where you can have a sandwich program, where 2 weeks is in the Netherlands and 1 week in Indonesia here. And we can also do, so if we have enough funding, then we can do a 1-month training also on different topics. So this will be really interesting for you, and later if you want more information, I can always share that with you. Okay, friends, so I would like to introduce you to the topic of resource recovery from waste gases. But before I really go into this lecture, first I would like to really say, at the end of the lecture, what do you learn, okay, or what do you get, or what knowledge do you get, is the fact that you will be able to realize the practical application of different bioreactor configurations and their role in resource recovery. Okay, this is really important, because we are not just focusing now on end of the pipe treatment. Okay, it's not only treating the pollution to maintain it according to the discharge regulations, but at the same time, we can also aim at recovering a lot of resources from these wastes. Then I would also tell you the importance of operating a bioreactor under its optimum condition, and to troubleshoot the reactor in case of an operational problem. So this is really important. If you want to do a MSc or MS or a PhD degree, at the end, you are not only, you're not going to be a technician, rather you will be a master of this bioreactor operation, and you should be able to troubleshoot the reactor. Okay, for example, troubleshooting means a reactor can have an operational problem with clogging. Yeah, it can have an operational problem with substrate inhibition. It can have problem with rupture of the packing material. It can have a lot of different types of operational problem, especially when you use if you don't use a mass flow controller, okay, to control the flow rate, gas or liquid flow rate, and you use a normal pneumatic flow meter, it's very highly likely that you will often encounter problems with a quasi steady state, because the influent is always fluctuating. Okay, so in wastewater treatment systems, or all these waste gas, wastewater, or systems that has waste materials, it's very difficult to achieve what we call a real steady state. Okay, because biological systems, they depend on the activity of the microorganisms. It also depends on the substrate's concentration, the substrate's composition. There are different things that we have to take into account. So troubleshooting the reactor is really important for a process engineer or a chemical engineer. Okay, now then I would also tell you some options where we have also recovered some of the valuable products, such as platform chemicals, or it can be a volatile, it can be VFAs, volatile fatty acids, or it can also be PHA or PHBs from wastewater. Okay, so at our institute, what we are doing in my chair group, we work with different components. We work with solid waste, we work with liquid digestates, and wastewater, waste gas, or biogas. So, for example, I will also give you some examples of biogas upgradation here in this work. But for example, if I am focusing more on the waste gas. So waste gas is nothing but the gas that comes out from any chemical industries, but they have carbon in it. Okay, they have carbon, but I'm not now talking about NOx or SOx. I'm talking about compounds that contain volatile organic or volatile inorganic compounds. It can be hydrogen sulfide, it can be benzene, toluene, xylene, it can be any of these waste gases. So these waste gases can usually, it's of course, if you have a very high concentration, you can always recover some of the carbon containing chemicals. But if it is not at high concentrations, the best is to recover some of the resources that comes out of that. And we also do biogas upgradation. So there are many ways where waste to energy projects have been very successful these days, and I think many of you will also be working on these topics. Okay, so waste to energy, it can be done by physical method, chemical method, or a combination of physical, chemical, and biological. So there are different ways in which you can look at the things. For example, here, if I'm talking about resource recovery panels, you can see critical elements or base metals or precious metals can also be recovered from end of the life electronic waste. Okay, for example, if you have this mobile phones, you can also recover a lot of gold, palladium, silver, copper, and all these things from printed circuit boards, mobile phones, then old vending machines, and also this cash ATM machines, okay, telecom servers. So there are a lot of examples for end of life products from where you can recover a lot of useful products. So when we talk about technologies, we are not only going to have one standalone technology, it's going to be the application of a lot of environmental concepts, technologies, and modeling tools in order to achieve environmental sustainability. Okay, so in our case, in most of our similar nature of experiments, we not only do work with bioreactors, but at the same time, we also try to combine some very nice advanced artificial intelligence based processes such as artificial neural networks or fuzzy logic, or we also try to use a combination of response surface methodology or ANN. Okay, so that is one way of looking at the things. And in many cases, the most important thing is also to have very sophisticated monitoring equipments. When you have sophisticated monitoring equipments, everything can be now made online. Okay, so with the help of GIS or remote sensing, you can now, you don't have to really go to the site and do all these measurements. Now with all this online monitoring and online technologies, you can quite intelligently control the performance of the system. So in this case, for our case, we are more going to focus on the bioreactor part. And in the bioreactor part, I will also give you some good examples of how to treat different types of industrial wastewater. Okay, so this is always a big issue that comes to us, also for me, because I'm also an editor in several journals. And one of the questions that is always asked is, did you try your reactor for any model or real industrial wastewater? You know, when you're working in the lab, you always try to prepare the synthetic system, synthetic wastewater or synthetic gas. But sometimes when the reviewer will ask you, did you try a real textile wastewater? But then the things becomes complex. You know, people don't, it's number one, it's very difficult to get a real textile wastewater. The second problem with the real effluents are the composition is not constant and it will vary day and night, and it's very difficult to find out what are the main compounds, what are the competing ions that are present, and many times the concentration, sometimes it's extremely high. Okay, for example, if you take olive mill wastewater, olive is not produced every day. Okay, it's a seasonal crop, and many times the COD of olive mill wastewater is in the order of 250,000 milligram per liter. Okay, and it's really difficult for any biological system to handle such high organic loading rates. So it's also important that we realize the importance of real wastewater and real biological treatment, also from not only from a research viewpoint, but also a little bit from the publication viewpoint. Okay, a few questions that I would like to ask, or you could still think about from yourself, because all this time I was talking about wastewater. Okay, now if you, this is much easier now. What are the different solid waste generated in your house or in your hostel or your dormitory? Okay, I think when you close your eyes, I think it's very easy that you can already identify what are the types of solid waste that you could generate. Okay, this is really important, because if you want to recover some of the resources, for example, you can recover a plastic, okay, a plastic bottle, you can recover glass from the house, you can recycle a part of them. Then you also, of course, you have a large fraction of organic components, okay, which can go for composting or other things. So once you know the composition, and once you know what are its properties in terms of physical, chemical, and biological properties, then you would be able to say what type of resources can be recovered from these solid waste. So one classical example of this resource recovery from solid waste is to get biogas. I think most of you know about this. It's about getting biogas from food waste. Okay, but still, when you look at the whole process, the process looks very simple of anaerobic digestion that starts with hydrolysis, acidogenesis, acetogenesis, and methanogenesis. But there are a lot of rate limiting steps, a lot of microbiology involved, and a lot of process parameters that are very sensitive to alkalinity and also pH. Okay, so that is where the real process dynamics comes into picture, and it's not just a direct conversion of food waste into energy. Okay, so there is process optimization, there is a lot of science behind the process. Of course, it's, when we talk science, then it's not only chemical engineering, but it's also biological engineering, biochemistry, and a lot of other things that are involved. And now we go to the third question: what resources can be recovered from industrial wastewater that is rich in its COD content? Okay, when you have very high COD, then of course you can go for very nice biological systems like a USB reactor, an upflow anaerobic sludge blanket, or these days you can also go for an expanded granular bed reactor. And of course, it's not only anaerobic processes, but there are also aerobic based processes which can be used for resource recovery. Okay, you can convert them into PHA or PHBs. You can also convert them into VFA fractions, and there are a lot of platform chemicals that can also be made from these COD. So it's not just COD that is directly converted into a product, but it's also a part of the fraction can end up in the growth and for cell maintenance. And now the point number 4, if I also ask you this question, name a few bioreactor configurations that you have learned in your undergraduate or postgraduate program, I think most of you will be able to say what are the different types of reactors. Okay, at least the batch reactor, continuous strip tank reactor, plug flow reactor, and of course CSTR in series and all. But now when we talk about real systems, they have different names. It can be in the form of membranes, it can be the strip tank type, it can be with modules, it can be different types of reactors. And one of this reactor that I'm going to tell today is, or at least 2 or 3 of them, a biofilter, a biotrickling filter. Then I will also talk about monolith and 2-stage systems. Okay, and then the 5th question is also what type of bioreactor or a reactor is very resilient. A resilient reactor means it's not a reactor that performs only for 30 days in the lab and we get a master degree or a PhD degree. No, that is not what we call a resilient reactor. Okay, a resilient and a stable performing reactors are reactors that are investigated over a period of at least 1 to 2 years at the laboratory level, and at the pilot level they are at least investigated for 6 months under varied operating conditions or harsh operating conditions. Then from the pilot we go to the semi-industrial, and finally we go for a full-scale scale-up. Okay, so it's not direct conversion of a batch reactor into a full-scale system. It's always stepwise procedures where you find so many different issues, especially with maintenance and also with the adaptability to the real life conditions. Okay, friends. So yeah, these are really some of the questions that you have to also ask to yourself. And it's also important, before you choose an appropriate technology, you should know what is the composition of the wastewater or the composition of the waste gas. Okay, so you might see now here it says Tampere University of Technology. It's not IHE Delft. The reason is because we have students who are in the joint degree program, so they travel to different countries, and one of our partners is Tampere, that is in Finland. Okay, friends, so the first case study is hydrogen sulfide removal under anoxic conditions. So now you may ask me, why should we remove hydrogen sulfide? So this is again a resource recovery based technology where you have biogas. In any biogas, it's not just pure methane. Methane is only 40 to 75%. Of course, it can be 60 or 55. It depends on the conversion efficiency of anaerobic processes, and it also depends on the organic waste fractions. Okay. But the biggest problem, before you want to subject this to heat and to produce heat or electricity, you have to eliminate a lot of the impurities that are present in the biogas. And one of the impurity is hydrogen sulfide, which can vary from 0.5 to 2%. So 0.5 to 2% means it is 5,000 to 20,000 ppm V. Okay, it is not 2%, is 1% corresponds to 10,000 ppm V. So they are quite very high concentrations, and such high concentrations can very easily corrode the pipelines or the whole piping network. And that will also reduce the calorific value of the fuel that is produced, and also the heat or electricity. So it's very important that we try to remove hydrogen sulfide. So in our study, what we did, we tried to use a very novel bacterium that is called a nitrite reducing sulfur oxidizing bacteria that we call as NRSOB. Here, this microorganism, it uses inorganic compounds as the energy source. So as you all know, hydrogen sulfide is an inorganic compound. Okay, it's not an organic compound, hydrogen sulfide. So in this case, this inorganic reduced sulfur compound such as HS or sulfide or elemental sulfur or thiosulfate is converted into SO4, that is sulfate, which can be recovered for sulfuric acid. Okay, and as you all know, the whole biochemical pathway, in order for the biochemical pathway to be successful, you need an electron donor and an electron acceptor. In this case, these microorganisms, the NRSOB, they use nitrate as the electron acceptor, and they convert it into nitrogen, whereas the electron donors are these inorganic reduced sulfur compounds. So we try to operate a very nice reactor configuration that is a biotrickling filter. I think most of you might have heard about this, or you might have even operated this biotrickling filter for wastewater treatment. But we did not use it for wastewater or waste gas alone, but we used it to treat both wastewater and waste gas. Okay, so that's the beauty of this technology, because you need a trickling liquid to keep the packing material here. For example, in this packing material has to be always wet. In order to keep the packing material and the biological NRSOB active, we used nitrate in the recirculation, whereas hydrogen sulfide was passed in an upflow mode. Okay, friends, now you may ask me, what is the contact time? Okay, how much time does the hydrogen sulfide spend within the reactor? It's a very important question, because in wastewater treatment systems, we talk about HRT, okay, the hydraulic retention time. We talk about 12 days, we talk about 2 days, we talk about several days. But here we talk about an empty bed contact time, and they are normally 2 minutes. Okay, so the whole gas, it passes from the lower end of the reactor to the top end of the reactor, all within 2 minutes. And I think 2 minutes is the maximum, and there are also high rate super systems now that can go up to as low as 4 seconds. Okay, so we call them as a high rate treatment technology. And now this is some of the profiles that we got. But interestingly, what I want to tell you is in wastewater treatment systems, we talk about carbon to nitrogen ratio. Okay. And we also talk about COD to sulfate ratio in the case of sulfur reducing bacterial systems. But in most of these, many of the systems, we talk about carbon to nitrogen ratio or carbon to sulfur ratio. But in this case, what we found out was the nitrate to sulfate, the sulfur ratio, or we call the nitrogen to sulfur ratio, was one of the most critical parameter that affected the operation of the filter. Okay, so this was again a small lab scale system which with the operating volume of 5 liters, and we did not operate it for 1 year, although we would like to operate it for a longer time. Because this was a part of the PhD work during mobility, we were only able to operate it for roughly 135 or 150 days. Okay, and what we found was also the nitrate. So the nitrate is in the liquid phase. The nitrate removals were quite high at the end, at least 80% of it was removed, whereas for hydrogen sulfide, we achieved around 60% removal. But 60%, when I talk about 60%, that is still a lot in terms of the loading capacity. It's not about removal, it's also about the loading rate. Okay, so my suggestion to all of you is, yeah, if you are looking for systems that want to meet the regulatory standards, then you look at what is the residual concentration that is coming out of the reactor. Okay, that is what matters most. It is not the removal efficiency or the loading. So it doesn't matter how much you pass, but if the concentration has to be within the guidelines of discharge, for example, 5 milligram per liter, you have to focus more on achieving those regulatory guidelines. It's not the 100% removal or 99% removal that matters a lot. It's also the complete load bearing capacity of the reactor. So in lab scale experiments, we usually subject the system to high loading rates, okay, or harsher operating conditions, so that we can go until the system is able to tolerate, and after some time it would probably also fail. Okay, so this is something that is really interesting to see, because in this way we also know what are the safe operating regimes of bioreactors. Okay, friends, then what we did, we had this nice NRSOB, but then we thought, instead of going for this microorganism, let us also take some microorganism from the hot spring, because in hot springs they have sulfur vents. You know, I think most of you might be aware of this. They have natural springs with sulfur in it. So we took one microorganism that was called a Parococcus strain, and we did also a few experiments, and we call this technology as bioaugmentation. Okay, so bioaugmentation is nothing but you add a new biocatalyst to an existing catalyst, and you try to enrich these new microorganisms within the bioreactor and also test the performance of the system. So now let me show you this nice bioreactor configurations which we have operated. You don't necessarily have to have one reactor with one configuration. You can have a biotrickling filter, you can have a stir tank reactor, all in the form of a vertical column. So in this case, you can see here, this is nothing but a kind of fluidized bed reactor with a packing material, and here is the packed bed reactor, and here is the trickling of the liquid. So in any case, for a fluidized bed reactor, you need liquid. So that liquid can come from the trickling liquid that is in this way. Okay, so a bioreactor configuration can usually be customized according to the land availability, and also the area, and also the process conditions that you would like to achieve. So in this case, I had mentioned to you that our idea was to remove nitrate and also sulfur containing compounds. Okay, so if you have some good idea of microbial ecology or fluid dynamics or also bioreactor technology, you can always integrate different bioreactors and find out its performance. So now I will take you to the second case study where we have methanol and thiosulfate under anoxic conditions. And this was also a very similar biotrickling filter configurations, except for the fact that methanol was added to this system in a gas phase. A gas phase is always from the bottom to the top, or you can also have it from the top to the bottom. But in this case, because there is trickling involved, we operated it from bottom to the top, and the trickling solution is from the top to bottom. And in this case, we did not go for hydrogen sulfide, because hydrogen sulfide is in the gaseous phase, but this thiosulfate, that is nothing but S2O3, 2 minus this thiosulfate, was in the liquid phase. So in this case, we have carbon, methanol that has a carbon, and thiosulfate that has the sulfur. So it was not nitrogen to sulfur ratio anymore. It was the carbon to sulfur ratio that mattered a lot in this system. And in this system, interestingly, what we observed was the removal of methanol was always high, okay, irrespective of the time of operation or the phases of operation. We were able to achieve nearly 100% removal efficiency. Okay, friends, now we also, I think I should also tell you about when people report 100% removal efficiency, it's very important that you don't say that it is 100% removed. It all depends on the sensitivity of your monitoring equipment, okay? It might not show you after a low detection limit. So it's always, when you write a paper, you better specify what was the lower detection limit of the system, for example, for methanol. So usually when although here I can say that it was close to 100%, I would always, when we write papers, we always report that it was greater than 98 or greater than 99, okay? It's so that is something that we have to also take care. But in the case of thiosulfate, we were able to achieve also 100% removal or greater than 99% removal, but it took relatively 10 to 15 days of time. But interestingly, in this study, the methanol, because it has carbon, it was converted into the volatile fatty acids such as acetic acid, propionic acid, isovaleric acid, then isobutyric acid, butyric acid, and valeric acid. Okay, so this was some of the interesting things that we found from this study, because we did not anticipate the pathway. But once we came to know that these were the end products, or these were the products of this bioreactor, now we have to find out ways how to recover them, okay? Because some of these platform chemicals are rather expensive in the market. So to get them into the purified form, and then to have them in the pure form is quite challenging. So what we tried to do was, I'm not showing the slide here, but after this step where we had VFA that was produced here, we took this broth that has VFA and we kept it into another batch reactor, and we added ion exchange resins. Okay, so these ion exchange resins have very high affinity to adsorb. So it's basically an adsorption process, and we use different types of resins. Although some of them are commercially a bit expensive, we use these resins, but at least it was a proof of concept to show that these resins, depending on the number of carbon atoms, they were able to selectively absorb isobutyric acid, valeric acid, or all these acids. Okay, so that is also one of the technology that you will have to look. It is not just getting the resources, but at the end we need to recover them and bring it back to the value chain. The third reactor system was a very novel system, but we did not continue this research because of many reasons. It's a monolith reactor. A monolith is nothing but a block, like a brick, which has a lot of vertical pores in it. And we took these monolith blocks. It's just like a brick, but it's made of ceramic. We kept it in a bioreactor. We kept it in an enclosure which was tightly sealed, and we added a fungi that was capable of removing styrene. Okay, styrene is a hydrophobic volatile organic compound, and we started to grow them. And as you will see here, this is the top view of the bioreactor. From the top, you can see all the sides of this reactor. These are the sides. We had a lot of wall growth, okay, because fungi can grow whenever there is a moist place and it has the the ambient pH. No, it has the desired pH for growth, and it has moisture and it has carbon. It starts to grow everywhere. Okay, it doesn't matter. It has to be a solid support. It will grow on the wall. It will also grow on the tubes. So that is something that has to be taken care, at least in the pilot scale. But we did not continue that further. And what we found was here. So in the past study, I told you the residence time was 2 minutes, but here we went down up to 19 seconds. Okay, but still the whole idea was to see the maximum performance of the system. The maximum performance, almost close to 99 to 100%, was achieved under certain conditions. But when we increased the inlet concentration, you can see here inlet concentration is here, even 1 gram per cubic meter, it really reduced further. Okay, and that is probably because of substrate inhibition, or it could be because of toxicity, or it could be also acidification of the medium. Okay, acidification means, as you all know, most of these reactions, they form sulfuric acid or hydrochloric acid as the end product. So when it forms these acids, then it will really lower the enzyme activity or the bacterial activity. So in this system, I had mentioned to you that there was a lot of growth of fungi all over the reactor, and what we also found was the pressure drop started to increase. Okay, so this is one of the biggest issue with all these packed bed systems. You have to monitor the pressure drop across the filter bed, and what we found was it increased, but still it was quite easy to clean. You only have to do a little bit of back washing with normal tap water. Okay, please don't use any other chemicals or other things. It's basically back washing, and within another few days you will still see good growth. So there is always maintenance time and a recovery phase for any of these bioreactors. It will take a little bit time, but usually these biofilters for waste gas treatment are quite resilient and they will recover. Okay, and increase in pressure drop is again a sign that says that the biomass has grown back. Okay, it doesn't mean that the biomass is completely gone, but we did not continue operating the system further because it always led to different types of pressure drops. But we also characterized this biofilm, and what we think was we should not have had a pure fungi here. We should have gone for bacterial growth, because the problem with some of the fungi is it grows as a mat, okay, or it grows at filaments, and when they grow as filaments and in such enclosures or such systems with cavities, it will immediately go and clog. So in such cases, it is often advisable to go for bacterial system. And the fourth case study is, the fourth. Sir, can you please tell me how much time do I have? Hello? Hello? Am I on the time, or is the time finished? I'm sorry. Hello?
Please proceed, Mr. Eldon.
Okay, yeah. So the case study number 4 is the removal of a mixture of methanol, alpha-pinene, and hydrogen sulfide. The reason why we wanted to try this is such a complex mixture of methanol, which is a hydrophilic VOC, alpha-pinene is hydrophobic, and hydrogen sulfide is an inorganic volatile compound. Okay, this is a very complex mix of compounds, and you may ask me from where do you get this? Such complex organic fractions and inorganic fractions, they come from the pulp and paper industry. Okay, as you all know, the pulp and paper industry is one of the highly polluting industry, very similar to a tannery. Okay, it has smell and it has also all these odors. So what we tried to do was we combined a biotrickling filter as the first stage, followed by a biofilter in the second stage. Usually biotrickling filter means it has a trickling liquid phase. So when you have a trickling liquid phase, which is almost similar to water, the system is capable of removing hydrophilic compounds. Okay, so hydrophobic compounds are not normally removed with high efficiency here. So we had another, what we could also call as a post-treatment step for removing the alpha pinene. So this was the first step that we did. The second step, what we tried to do was we took the biomass from here. From the second step, we added them all here as a cocktail, and then we operated only a single stage system. So in research, you can always play around with different reactor configurations, different type of feeding modes. It can be a fed batch, it can be continuous, it can be intermittent, it can be shock load, it can be different types of feeding strategies can be done all at the research. Okay, but in practice, it's quite difficult to go and at the industrial level to go and do all these fine tuning, because industrial situations are normally, they are not in steady state concerning waste gases. Okay, waste gases concentration is always fluctuating. It depends on the process, it depends on the chemicals used, it depends on what is the source of the polluted gas mixture. So this was the system that we operated in the second step. It was as one stage system. And now concerning the biomass, it's very important that you should also select the correct type of biomass for each specific pollutant removal. So in this case, we had three different types of biomass, three different types of pollutants. So we took three different types of biomass. One was Candida boydini, Ophiostoma species, and autotrophic hydrogen sulfide removing microorganisms. So this is how you will see after a few days of operation, a lot of biofilm will grow on the PAL ring. This is nothing but a PAL ring that is covered with excess biomass. What we found out was, so this was a system that was operated for more than 400 days. And what we found out interestingly was methanol was very nicely removed, irrespective of the concentration of hydrogen sulfide or methanol. The reason, alpha pinene. The reason is methanol is a hydrophilic compound and it is quite easily degraded by bacteria or a fungi. But with the help of, for the case of alpha pinene, you can see the concentration fluctuates up and down. Okay, to a chemical engineer, if I show this figure, is it steady state? They will really laugh at me and they will say that this system cannot be considered at all. You know, the reason is, yeah, there is no steady state. There is not even a quasi steady state in such systems. But you should also acknowledge the fact that it is not a single stage. It is not a single pollutant. It is not a single microorganism. It's a mixture of pollutants. It's a mixture of microorganisms performing the job. So usually in bioreactor systems or this type of biotrickling filters, we always expect what we call a synergistic effect or an antagonistic effect due to the presence of one pollutant. Okay, so the presence of one pollutant can enhance the removal of other, or it can also negatively affect the removal of other pollutant. So this is what we found here. And in the case of hydrogen sulfide, yeah, at least it was much better than the removal of alpha pinene. Okay, so if you ask me to rank the order of removal, it is always it's always methanol, followed by hydrogen sulfide, followed by alpha pinene. Okay, friends, so now, based on all these nice experiences, operating single pollutant, multiple pollutant, then also looking at different reactor configurations, looking at different operational strategies, I would like to say, or like to enforce here, that biotrickling filters are quite versatile systems. Okay, they can handle a steady state, they can also handle a transient state operation. A transient state means the load or the concentration is not constant throughout the time. Okay, it can vary up and down, or it can also go stepwise depending on the process, or it can go high up to the morning shift is over. Then if there is no night shift, then there is no pollutant that is coming for, or no waste gas. So if you ask me the question, can these systems operate 24 hours a day? The answer is yes, because some companies, they don't have a 24-hour operation in 3 shifts. They only have a morning shift or probably 2 shifts. The third shift, the microorganisms need some air. Okay, because without air, there is no oxygen, and the microorganism will, the activity will decrease. So in such cases, the ventilation air, the ventilation air from the factory is normally passed into the biofilters. So you don't necessarily need to have the waste gas all the time. At least to maintain the activity of the microorganisms, you can pass the ventilation air during the night time. And the good thing about such biotrickling filter systems are resource recovery is possible from waste gas and also wastewater in the same reactor configuration. So you can treat both these pollutants in the gas form and the liquid form within one bioreactor configuration. But for a company, that really matters a lot, because it saves the land area. Okay, so that is something that they also take into consideration. And also these days, with the advent of a lot of new technologies, technologies, and also the growing internet now, process control is really important for all these systems. And biotrickling filters can be fitted with numerous sensors. Okay, so what we are doing was only a very small column, but in real systems, they have very good sensors, and you don't really have to go to the site. You can always do everything, even now, with a mobile phone. Okay, so these are really robust systems that can be intelligently controlled with good advanced automation system. So now the take-home message. At the beginning, I was telling you about the objectives, the learning objectives of this lecture. But now, at least for all of you, I would like to remind you a few take-home messages before you go for choosing a bioreactor configuration. Okay, so it can be a small vessel like this, which we call a batch reactor. And before you go to select a batch or a continuous process, the first thing you have to know is what is the gas composition and its characteristics. The reason is some of the gases can be acidic in nature. Okay, they can be acidic, some can have chlorine, some can have other poisonous gases. So it's very important you need to identify its characteristics and its composition. Now comes the second question. Why do you want to treat, and what is the purpose of the treatment? Do you want to only go for meeting the regulatory standards? Okay, the pollution control board might come. Do you want to meet that criteria, or do you want to really get a biogas of high quality, or do you want to do some resource recovery based approaches? So it all depends on the purpose of your treatment. Okay, so that is something that you have to be really careful. The third and fourth is the loading pattern. As I told you, maybe in the night there is no pollutant that is entering. You should be able to know what are the loading patterns and the parameters to be monitored. It's very important when you start a reactor right from day one. Okay, it's important that you monitor all the parameters of interest. It doesn't matter even if the leachate contains all these competing ions, magnesium, calcium, all these things. It's very important that you measure all these parameters. So I'm not only talking about industry. Now, if you also want to publish, the reviewer might ask what is missing. Okay, it's normally now the tendency that they don't ask questions to you what you have done. They ask questions what has not been done. Okay, so they always look for all the loopholes. The editor also looks for what is not done and how to reject the paper. So it's important that you do a good planning of parameters. And from a process technology viewpoint, you should also know how to troubleshoot. Okay, so that is where the real expertise comes. You are not a technician now, you are an operator of the whole plant or the reactor. So you should know how to troubleshoot, how to maintain the proper conditions, or how to do this process control integration together with the bioreactor. And at the end, it depends on the space. Sometimes a single system cannot treat all the pollutants, and in that case you might have to go for a pre-treatment or a post-treatment. So in many cases, a post or a pre-treatment system it's not necessary to have a biological system. You can also have adsorption. Okay, adsorption is a really good system where you can absorb the gas phase pollutants, and when it is not when the bed is exhausted, you can always desorb it and then pass it again to the biofilter. So I'm not telling that to pass it to the air. You can still pass it, desorb, and treat it. So such systems can be very easily customized as a standalone treatment system or an integrated 2-stage system. Okay, but we don't go for 3-stage or 4-stage. The reason is it will cause a lot of head loss. Okay, so usually it is a single stage or a second stage or a 2-stage system. Okay, so once again, thank you so much for your very kind attention. And if there is a chance, I would like to welcome all of you to Delft for at least this tailor-made training programs. Or we also have short courses. You can have a look at the IIT Delft website. We have a lot of short courses that will start from September 2021, and I hope the visa for Indians will be relaxed at that time. So yeah, thank you so much. And if there are questions, I would like to answer to your questions. Yeah, thank you so much.
Thank you for your amazing lecture, sir. Participants, if you have any queries, you can ask now.
Yeah. Okay. Now I'm very sorry. I only see the questions now. Okay. So there is a question from Kavita. In case study 4, your SRT is more than 1 year. Is there a chance to reduce SRT for removing particular organic compounds? Okay. So here we don't use the word solid retention time. Okay, that is not a parameter at all. We only use empty bed residence time, and the biomass concentration is usually after 2 or 3 months of operation. It's normally constant, and we normally also do a little bit of backwashing when we observe pressure drop. And in waste gas treatment system, SRT is not a factor. Okay, unlike in wastewater treatment systems. So the second one is parameter optimization is critical in ASP. What are all the steps to be taken to control the process? Yeah. So can you tell me what is ASP? Is an activated sludge process? Yeah.
Activated sludge process.
Okay, yes, yeah, I fully understand that parameter optimization is very, very important. And also in ASP process, there is always sludge wasting or sludge recycling also, and that will maintain your SRT. And of course, temperature, pressure is not a factor, then pH, then MLSS concentration, organic loading rate, the aeration. So in an activated sludge process, yes, there are so many other very important parameters that you have to take care. But in a trickling, because I did not speak about ASP in my presentation, but we can also operate for hydrophilic systems, we can operate a strip tank bioreactor. Okay, we don't use the word ASP here, but we can call them as a continuous strip tank bioreactor. And these days, there is a bioconsole which we can buy from direct biotechnological companies. So we don't really need to worry much about parameter monitoring, but optimization, yes. So we need to decide, at least during the first 6 months, you have to spend some time on parameter optimization. But the most important parameter is the loading rate. Okay, it's not the temperature, because they are mostly mesophilic. pH is normally in the range of 6.5 to 7.5, and but in the case of fungi, if you have fungi, then you can go up to 4.5 pH. Okay, but apart from that, nutrient limitations or other things, they are not a big problem for biofilter operation. Okay, there is also a question about energy consumption. Yeah, the energy consumption is not a very big issue here, except the pumps that are used for trickling the liquid, and for if you are going to fit with sensors, there are no other moving parts. Okay, as you all know, for an ASP process, main electricity or power requirements comes from the agitator and also from the aerator. But here we don't have an aerator because we are only passing air to be treated that already has oxygen in it. So specific energy consumption, yes, it will be nice that we could do that, but for waste gas treatment systems, it was never an issue. Okay. Okay, is there any other questions or comments? Okay. If you don't have questions, you can also give some advices on how to operate, or you can also share your experiences, which I think is very interesting for all of us.
Good afternoon, sir. I am Divya.
Yes.
As an Anoxic revision student, sir.
Okay. Hi, Divya. Yes. How are you? And how did you come here now?
Sir, actually, I am working as a professor in here, sir.
Okay. Yeah.
Last year, sir.
Eldon, he joined recently. Eldon, recently he joined. Recently joined.
Okay. Yeah.
Okay.
Yes, Divya. Yeah, please.
Yes, sir. That 4 case studies are covered. It's really all kind of bioreactors, sir. How you given in such extraordinary lecture, sir? It's really amazing, sir. Thank you so much for your lecture for in this SVC, sir.
Okay, thank you, Divya. And I also know that you and Ravi sir, together with Professor Pakshirajan, you have also developed several bioreactor configurations. So all this it came from experience. Okay, at the beginning we only operated biofilters. We did not go to biotrickling filter because biotrickling filter, it has a little bit more complex structure. And later, based on all the experiences, now at least I can tell my students, because now I'm not going to the lab to do any experiments. I can only guide students. So at least all the experiences that I had, I can tell them to avoid, which gives them, which actually gives them a rather smooth start for a PhD. So many of these PhDs, as I told you, as I had mentioned, we have a mobility program, and the PhD is only for 3 years. Okay, so within 3 years they have to go to 3 countries, they have to start experiments, they have to operate the reactor, and at the end, there is also publications. For 3 years they have to publish at least 4 papers. So there are some very tough criteria for all this. So based on my experiences that comes from my PhD on biofilters, then I started to develop it to a different field. But if you operate one reactor for wastewater, that is more than enough to get experiences for operating in biotrickling filter. You can operate if you want, you can operate a rotating biological conductor. You can operate 2-phase systems. Any type of system is possible.
What about
Yeah. So you don't necessarily have to operate biotrickling filter. If you operate one bioreactor, you can extend it to that.
Yeah. Thank you so much.
Yeah. Thanks, Divya. Yeah.
Any other questions, please? Lavanya?
Okay, sir.
You can proceed.
Okay, sir. Thank you, sir. Let's move to the session now. So participants are requested to join in their respective tracks.
Thank you, Eldon, very much. Thank you, Eldon. Thanks a lot.
Thank you, and all the best, and very good luck with the program. Yeah, for today.
Okay. Thanks a lot, Eldon.
Thank you. Yeah, bye.
Thank you.
Thank you, Dr. Eldon. Thank you.
Yeah, thank you. Bye.
Bhaskar sir. Bhaskar sir. Sir, ಇದೇ ಸೇಮ್ ಲಿಂಕ್ ಲದನ ವ್ಯಾಲಿಡಿಕ್ಟರಿ ಫಂಕ್ಷನ್